So thank you for joining us, Francesca.
Thank you so much for the invite. Yeah, I'm looking forward to, talking about this work. So yeah, should I dive in now, or give you some more time to start the live stream?
Yeah, the live stream is a go. Just was able to start it now. So yeah, you're ready to go whenever you want. Oh,
Okay, great. So yeah, so my name is Francesca, and today I'm going to be talking about short privacy-preserving proofs of liability. And this is joint work with Kautar, Yakov, and Angelo, all of whom are at IBM Research, and this was done while I was interning there. So we consider the following scenario. So there's a cryptocurrency exchange, for example, with two customers, and these customers purchase 10 and 20 Ethereum, respectively. And so the exchange thus claims that it has a liability of 30 Ethereum to these two customers. In other words, it owes a total of 30 Ethereum to all its clients. Now, what if the exchange is malicious and it decides to not include its liability to one of the customers? And so now it's claiming a total liability of 20. Well, this is, in fact, a very real problem with disastrous consequences that we have seen play out time and time again. Most recently, FTX, which infamously filed for bankruptcy in November of 2022, I believe. So this was actually very timely because it happened around the time that we were kind of in the middle of working on this project. And so for some context, essentially FTX was reinvesting money into another company. And so when customers clamored to withdraw like $6 billion, they didn't have the money to actually cover all the withdrawals. So they had to file for bankruptcy. So there's this big question of how can we prevent such behavior? And how can we detect such malicious behavior earlier? So one promising solution is to use something called a proof of liabilities. So the idea is to have the liable entity publicly commit to its liability, for example, on a blockchain. And then this is done in such a way that users can later request a proof that the total claimed liability is correct. So, a customer should be able to say, is that total correct? And the exchange should be able to provide a proof that they can then use to verify the total. And we would also like an additional functionality. We would like that the customers can also request a proof that the total amount includes the liability owed to them. So once again, the exchange should be able to provide a proof that the customer can then verify. And in particular, what we also want is that if the user's amount is not included in the total and that user requests a proof, the proof should not be valid with all but negligible probability. So companies that store currency on behalf of clients, for example, an exchange or a commercial bank, may be audited to ensure financial solvency. In other words, that the clients can retrieve their deposits in full. And the way this is traditionally done is by having like third-party auditing firms come in and look at all the data and verify that, these transactions are correct. But this is problematic for a couple of reasons. It's very centralized. It's not privacy preserving, right? Because all the data is being shared with this third-party auditing firm. And it's also costly and time inefficient. So, we still have this problem. So companies may try to fudge their numbers and claim solvency, even when they do not have the necessary funds. So one decentralized way of proving that these companies are solvent is to have a proof of liability. So this cryptographic primitive that solves half of the solvency auditing problem. And the goal is to prove that the amount the audited entity owes to its client is correct. The other half of the problem is called proof of reserves. So the goal of that is to prove to the clients or customers that they have sufficient funds to cover those liabilities. And so together, POL and POR form what we call a proof of solvency. But today I'm just going to be presenting our scheme for POL. Now, POL is useful in several cases or applications. Of course, proof of solvency, as we've been talking about. In fact, in a consultation with, I believe, the European Central Bank, privacy was actually cited as like one of the most important design features of a CBDC. So this is, POL and its privacy preserving kind of approach to auditing is very useful in this case. Okay. But more generally, POL is useful in any scenario in which the prover is not incentivized to increase its liability. So this is also useful in things like reporting COVID cases, right? Because maybe a country or a company that's reporting COVID cases, it's not incentivized to report a higher number in a lot of cases, right? So they might try to, claim fewer cases than actually there are. And then another example of such a scenario where the prover doesn't have incentive to increase the liability is negative voting. Okay. And then lastly, I just want to make the point that using this privacy preserving approach can also be helpful in complying with data privacy legislation, things like the GDPR and California CCPA. Okay. So now I'm going to give a little bit of overview of the POL landscape. So there are several schemes that have been proposed over the years, starting with the Maxwell scheme in 2014. So this first scheme was based on the Merkle tree, and the idea was that the leaves of the Merkle trees corresponded to the liabilities of the users, and the inner nodes were essentially hashed to the sum of the children. And so this was proven insecure in later work, and this follow-up work essentially identified the flaw, fixed it, but they still leak the number of users. In 2015, there was provisions. Their scheme used Pedersen commitments, and they took a flat list approach, so there were no Merkle trees or no tree structures. And this resulted in publishing a large amount of data to the public ledger, which is something we were looking to avoid. Then in 2020, there was Daypol. So this scheme hides the number of users. They used a sparse Merkle tree, but the padding strategy was actually flawed and was fixed in follow-up work. However, I just want to point out that all these works, with the exception of provisions, was based on the Merkle tree. And so they all had these authentication paths of essentially log-based too. And so what we do in our work, so here's a table that kind of summarizes everything, all the complexities of the previous works and our work. So as you can see in our work, we do achieve full privacy. So we don't leak anything about the honest users. And all our proofs are log-base n, which is a parameter that's adjustable. And I'll be going into more detail about how we do this in the later parts of this talk. Okay. So in this work, we introduce a novel data structure, which we call the sparse summation Merkle tree. We present 3 new zero-knowledge protocols over vector commitments. We optimize these protocols to support aggregation. And then we also implement our scheme under 2 realistic use cases. Now, for this talk, I'm going to be introducing our data structure. I'm going to be talking about 2 out of the 3 protocols, and I'm also going to be sharing some of our experimental results. But if you're interested in more details, I encourage you to maybe ask after the talk or check out our paper. Okay. So a little bit more background about the problem. So we have these 2 entities. We have the users that are the parties who store their assets with the organization. And then we have some prover that operates on behalf of the organization and is the entity liable to the users. And the prover's goal is to prove to the users that their liabilities are included in the total. So the audited entity does not have any incentive to increase its liabilities. This is a really important assumption that's made in our work and also all the prior work on proof of liabilities. And the question is, how can we ensure that the liabilities to each user are included in the total? And how can we do so efficiently, so with short proofs, and while also ensuring privacy to the users and minimizing leakage? Just going to quickly touch upon the threat model and assumptions a bit more here. Okay, so I already mentioned 1. We assume that users establish a secure communication with the prover. The adversary may corrupt users and try to learn information about the non-corrupt users. So this assumption is important in how we define privacy, which I'll talk a little bit more about in a couple of slides. And then we also make this assumption that there's some public bulletin board, could be instantiated with a blockchain, but essentially there's some mechanism through which this public data can be published and that all the users have the same view of this public data. And in particular, we want our scheme to achieve the following security goals. So firstly, back to our small example here, if the prover generates the proofs honestly, then they should be valid with probability 1. On the flip side, if the prover is malicious and it did not include the correct liability to some user, and that user requests a proof, then that proof should only verify with at most negligible probability. And then lastly, we define privacy with respect to the view of the malicious users. So as I mentioned, the adversary can corrupt some subset of the customers, of these users, and we define privacy with respect to what these malicious clients or users can learn about the honest users. And so, for example, if privacy, if the scheme is not private, then that means, the malicious users can learn essentially the whole database. And then if, in the best case, if the scheme is fully private, then the malicious users learn nothing and the leakage is just the empty set. And so actually our scheme achieves full privacy, so the malicious users cannot learn anything about the honest users. Okay, I guess now maybe would be a good moment to take a quick pause and see if people have questions about kind of the setup and the problem statement.
I have a question if you could go over the integrity property again, and I guess I'm thinking ahead to wondering if users need to actively be involved in checking their own accounts or whether you get sort of automatically done for everyone.
Yeah, okay. So essentially there is this kind of probabilistic yeah. So essentially the correctness of the liability kind of hinges on like the honest users all checking their liability. So yeah, this is, you know, I would say maybe a bit of a limitation. And I think, you know, trying to see if there's a way to have better guarantees with only a subset of the users checking is like a really interesting open problem. But yeah, really we kind of would require to be fully certain that the prover isn't cheating. We would require that all the honest users check their liabilities.
That makes sense. How does it show up in the like statement of this? I guess when you went over it, I didn't end up recalling whether I thought that the definition sort of suggested it or not. So
For the soundness and completeness, you're saying?
yeah, especially on this kind of issue, like I'm trying to learn
Yeah,
how to
so
recognize in someone's statement whether it kind of alludes to this or not.
basically, the completeness and soundness, when we like define it formally, it's with respect to the honest users. So it's like if like whatever subset of the honest users that check their liability, essentially the total liability should not be the total claimed liability shouldn't be like smaller than the sum of the honest users checking. So yeah, that's kind of how it shows up in those definitions. Both definitions are like specifically defined with respect to the subset of users that are checking and that are honest.
Cool. I'm really happy with that.
Great. So great. So I guess if there aren't more questions about kind of the security or background, I guess I can continue on with the scheme. So I'm going to give a bit of a high-level view of our scheme, and in particular, the data structure that we use to achieve this. Okay. So in a nutshell, we introduce a novel data structure, which we call the sparse summation Merkle tree, which we use to accumulate liabilities. And so the advantage here is that this results in shorter authentication paths. It hides the total number of users. It further mitigates leakage and benefits from the efficiency of vector commitments. So the two main building blocks for our scheme are collision-resistant hash functions and vector commitments. So in particular, a vector commitment can be kind of viewed, I guess, as a generalization of like a standard Pedersen commitment, but essentially it allows us to commit to an ordered sequence of values such that this commitment is compact. And then we also want to be able to essentially open up the commitment with respect to a specific index. So let's say I want to prove the value that's at like the first index as an example. And the requirement that we have on vector commitments is that they satisfy position binding. So the prover should not be able to open up a commitment at some index I to two different values. Now, before I talk about our data structure, I want to kind of take a step back at a Merkle tree. And, you know, as I'm sure some of you are, you know, many of you are familiar with, this is what, you know, a Merkle tree looks like. This is what most of the earlier POL works are based on. And so the idea here is that you have these liabilities, each associated with leaves of the tree. And then the inner nodes are hashes to the liabilities, or hashes of the children. Okay. And then if you want to prove that some liability is contained, then you can provide all the nodes along the path from the leaf to the root and the sibling nodes. Now, a Verkle tree is like a Merkle tree, but what it does is it replaces the hash values of the inner nodes with vector commitments. So each inner node is labeled with a commitment to an n-length vector, and each index of the vector corresponds to one of the n children or the hash of one of the n children, depending on whether it's like the parent of the leaves or further up the tree. Now, one thing I just want to, point out here is that unlike Merkle trees, which are inherently limited to a binary tree structure, Verkle trees can take on a n tree structure. So, by increasing this parameter little n, we can get trees that are flatter, and so we have shorter authentication paths. I guess the one point here is, because someone might ask, well, then we can just make little n, arbitrarily large and get trees that are very, very flat. The one trade-off here is that, as you increase the size of the vector commitment, the public parameters also grows. But yeah, so we're able to get these flatter trees. So that's nice. Now kind of building on that, a summation Verkle tree is a Verkle tree whose inner nodes are labeled with an additional commitment to an n+1 length vector. So the first n indices correspond to the values of the children. So for example, here the commitments would be to L0, L1, and L2, and then the n+1th term would be the sum of those children. And then looking at the root here, then this first index would correspond to the sum of the first child, the second index, the sum of the second child, and so on.
Sorry, just quick. So when you in the node V0, is that meant to be summation from 0 to 2 then?
Yes, good catch. Sorry, that's a typo. I'll have to make a note to fix that. Yeah, exactly. So this n+1th term should be the sum of all the children. Yeah. Great. Yeah, so what this essentially allows us to do is not only commit to the values, but also commit to the sums of those values, which is kind of analogous to what some of those earlier works based on Merkle trees were doing, because those inner hashes were essentially hashing the sum concatenated with the liability values. So yeah. Okay. And then to kind of get to the final data structure, a sparse summation Verkle tree is a summation Verkle tree over a universe U. So U could be exponential in size, but in particular, the leaves of the tree are 1-to-1 with the elements in U. However, we're going to assume that most elements in this universe are not actually in the membership set. We don't care about them. So the tree can be represented more compactly by using only the necessary nodes. So for example, if the universe is the universe of all possible social security numbers, then the universe would be like, for example, all possible 9-digit numbers. But in reality, we only care about the social security numbers that are actually assigned to real people. And so we can just represent the tree by storing only the leaves that are mapped to actual people who have been assigned a social security number, and then all the nodes that lie along the path from those leaves to the root. And so the way our scheme works is we have this SSVT, and users are assigned to leaves of this tree by hashing their ID. This is where we need the collision-resistant hash function, since we assume the universe is, sufficiently large, and we're using a collision-resistant hash function. Then we can assume that users won't be mapped, like two distinct users won't be mapped to the same leaf. And now, when a user queries for inclusion, what it receives is the authentication path. So it receives all the vector commitments along the path from its leaf node to the root, together with some zero-knowledge proofs that check the following. So it's going to check that the values are positive, that the sums are correct, and that the sum of the child node is a term in the parent's vector. So pictorially, what this looks like, I'm going to kind of step through those proofs again visually. So here's our tree, and user with ID 0 queries for its liability. And so it gets back all the vector commitments that lie along the path, together with the following proofs. The first is a proof that all the values committed to in that path are positive. So this is essentially ensuring that the prover doesn't try to slip in a negative value somewhere along there to decrease the liability. The other thing we're going to check for is that the sums are computed correctly, that the n+1th term is indeed the sum of those previous n values. And then lastly, we're going to provide an opening equality argument. So what we want to show is that, for example, L0 is in fact the first index of the parent, and then that this L0 plus L2 term is in fact in the first index of the parent. So this kind of shows like chain of containment, I guess you could say. I guess it kind of shows that, these vectors are actually connected in some sense. Yeah. I guess that's also in addition to these W vectors, which are like hashes of the children. Okay, so these are the proofs we care about. Okay, and the privacy of the scheme follows from the history independence property of our tree, and from the zero knowledge of the inner product arguments, and the vector and the hiding property of the vector commitments. So yeah, I realized I didn't really talk about inner product arguments. That'll become clearer kind of in the protocol section, but essentially we're using inner product arguments to instantiate all these zero knowledge proofs. Okay. So now I'm going to
Quick
talk
question,
about
actually, on the previous slide, is the actual value of L1 plus L2 leaked, or L0 plus L2 leaked to the user who's checking for, say, L1 or L2?
No, so those values are not leaked.
Okay, thank
Yeah.
you.
Basically, I kind of left out all the hiding essentially from this presentation, but in the paper, what we actually do is like all these vector commitments should have like an additional term with some random value. So all of these commitments are have this hiding property. And we don't want to reveal like the actual sums other than maybe the total liability to like any of the users. Yeah.
Perfect, thank you.
Thanks. Great. So yeah, maybe I'll also take another pause here to see if there are any questions about the scheme, because now I'm going to be switching to talking about our protocols a little bit. Okay.
I'm interested in how clients would get their witness. Like, I get that they need to basically provide their witness through a query, but yeah, I also have something in mind later, which is like how light clients might do that and whether some kind of oblivious search is needed. But maybe it's already clear at this point, like just what their witness needs to be.
Yeah, okay. So I guess for the different proofs, the zero knowledge proofs you're saying? Yeah, so I mean most of them, so let's see, the witness is, let me quickly take a look to maybe give you an example for like one of the proofs that are provided. Um, yeah, so I mean, basically, they're getting the like the vector commitment will be the instance, and then the prover, so the organization or the prover, I guess, has access to these values, and then they'll yeah, I guess through this interaction, then the user can be maybe convinced. But yeah, I mean, I guess your question about how the users are getting, yeah, maybe could you maybe ask your question again? Sorry.
Yeah,
I
sure.
think
I mean, the problem's kind of inspired by what happens in Zcash and Monero, and I think anything else where users have to maintain a witness in this tree, but the tree overall might be modified, especially with these like try things. So as a result of other people's data being added to this tree, the witness of a user may now change. So they have to be either constantly updating their witness,
yeah.
processing blocks as they arrive, or they have to be doing some, protocol with a query node, but then that becomes might point to further privacy hazard.
Yeah, yeah. So yeah, I guess looking at this kind of dynamic setting is I guess really important in practice. And we didn't actually do like go into too much detail in our paper. Kind of what we said were like, yeah, vector commitments are easily updatable, which they are, and there are like a lot of works that kind of look into updatable vector commitments. So I guess kind of like to answer your question, we kind of said, yes, it's updatable, vector commitments, can accommodate this dynamic setting, but we didn't actually look into the specifics of it. And I think I did see a recent work on like dynamic POL that does this more formally. So I think they're like the first paper that really looks into this setting of like how can you handle like all these liabilities that are being updated over time. And then they also provide some like definitions. I think it's on ePrint right now. I'm not sure if it's published yet, but yeah. So I guess in the context of our work, I can't really say too much though about updating. Yeah.
Okay, yeah, that's perfect. That clarification helps me feel pretty confident, and the reference is really cool. Yeah, thanks.
Yeah. So the protocols. So our scheme supports the black box use of any range protocol, sum argument, and opening equality argument that takes as input Pedersen-like vector commitments. So so to kind of say a quick thing about the Pedersen-like vector commitments. Fortunately, a lot of the vector commitment schemes out there do have the same kind of structure where you have like, G to the 1 raised to like M1 times G to the G2 raised to M2 and so on and so forth. So it's like a product of these group elements, each raised to one of the values in our vector. So that'll become clearer kind of why I'm like making this comment. But yeah, for completeness, we do provide instantiations of all our protocols. We make use of these vector commitments and an inner product argument to essentially build our zero knowledge proofs. And then we also support batching of proofs for all three. Okay, so inner product arguments. So the way an inner product argument works is we have, for example, these group elements, G0 through G to the n-1, and then H0 to Hn-1. And in particular, an inner product argument allows a prover to prove the following. So if I have two vectors, A and B, and we commit to these vectors using those group elements, so we take G to the 0 raised to A to the 0, dot, 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 G to the n-1 raised to n-1. Okay, so we're essentially just raising these group elements to the values of our vector. And then we're going to do the same for our vector B. And so now we have this commitment to our two vectors. And we want to prove that these two vectors that we committed to using P, or sorry, these two vectors that we committed to, whose commitment is P, that their inner product is equal to some value C. Okay, so the verifier gets P and C, and the prover will, try to prove that it has these vectors A and B. And there's a very nice paper that provides inner product argument, bullet proofs. We use it in our instantiation. The thing I want to say is there are existing inner product argument protocols out there. And so we're just going to use them as a black box, essentially. So we're going to try to turn all the things we're trying to prove into inner products, and then we can just, chuck them into an inner product argument and generate the proof this way. So what I want to kind of give you guys now is some intuition about how we turn these things we're trying to prove into inner products, starting with the sum argument. So suppose we want to show that this vector v, yeah, I know I kind of switched over to using slightly different notation here, but this bold v is a vector, and we want to show that the first n terms sum up to the n+1th term. So we're just going to rearrange this now. And what I want to point out here is that we can prove that, well, if this first equation holds, then actually the inner product of v with the vector of all ones, where the final term is a -1, -1, should be equal to 0. And so essentially, if we can commit to this vector v and this other vector of 1s and -1, then we can use an inner product argument to show that, we know v and its inner product, is 0. Notably here, this is not zero knowledge. So what we do is we blind v before calling the inner product argument. what that looks like is essentially we have another term here raised to some randomness to blind the vectors. Okay. But yeah, so this is the sum argument in kind of like this inner product form. Okay, so how can we aggregate sum arguments? So now suppose we have multiple vectors that we want to prove this property for. Well, we can extend this technique using a random vector D. So we take we sample a vector of length m, and what we do is we take our vectors that we're trying to prove this for, turn them, we essentially concatenate them into like a matrix, and then we matrix multiply D with this matrix of values to get this new value C, this new vector C. And so what we observe is that if the VIs have this form that the first n minus one, sorry, the first n terms sum up to the n plus 1th term, then actually what this implies is that when we take the inner product of C with the vector of all ones n minus 1, then we should also get 0. So in this way, we can essentially prove that sum argument for all the vectors along the authentication path using one inner product argument.
So this, by the way, is just a random linear combination type like technique, right? And
Yes.
I guess this would hold if D is like not adversarially chosen. Like there are some like small probability of choosing D in a way that you get 0, even like it's not a fully if and only if statement, right? So how do you choose the D? Is this like using some sort of PHMER argument?
Yeah, so how is D chosen? Yeah, I think if I remember correctly, yeah, I think it is. Yeah, there is this, like basically what we do argue, like even if it's honestly chosen, right, there's still this probability
Yeah.
that we get 0 even if it's not of this form. So yeah, but yeah, you can use something like the Fiat-Shamir argument to choose D in such a way that you're more confident, I guess, that it's not adversarially chosen.
Okay, thank you.
Yeah. Mm-hmm. Yeah. Okay. Um, Great. So that was for the sum arguments. So now I'm gonna quickly touch on range proofs. Okay. So suppose we want to show that the entries of V are positive, right? This is what we want to essentially show, that all the liabilities along the path are non-negative, specifically. So, well, our starting point is this vector commitment to the values. And what we're going to do is we're going to apply this iterative reduction technique, the details of which we don't actually go into too much in our paper either. This is taken from Boodle et al. But the idea is that through a series of, I guess, some rounds of interaction, or you can use the Fiat-Shamir heuristic to make it non-interactive, but essentially you have these challenges. And at the end of this reduction, we end up with a commitment U that is a commitment to a single field element. And this element is a function of these challenges and the original values. Sorry, it's a function of the challenges, and the coefficients of this function are the original VIs. Okay, so we have our commitment U, and we're also going to commit to the bits of the VIs. So this is our capital B here. So to kind of keep track of everything, we have our commitment U, we have our commitment V to the original values, and then we have a commitment B to all the bits of those values. And we're gonna, try to use these to prove what we want. And in particular, what we want is to try to relate the bits that we committed to in that capital B to this field element U. That's a function of the challenges, and the coefficients are the original values. And so essentially what we did in our paper, we kind of followed this iterative process to try to pin down exactly what that function looks like. And so once we know what that function looks like, we can essentially write U as the inner product or the dot product of the vector of bits and some vector D, where D looks essentially like this. So we have these FIs, and then so for each DI comma J, it's like some coefficient multiplied by 2 to the J. Okay. And then B, of course, comprises the bits of the vectors of the vector. Now, it's not enough to prove that U is indeed the dot product or the inner product of B and D, but what we want to also show, to be sure that the VIs are positive, we need to prove that the BIJs are actually bits. So kind of looking at this first half here. Okay, so how are we going to prove that the BIJs are bits? Well, if they are indeed bits, then these two equations should hold. So let W be the bit complement of B. And so if we take W and we subtract the all ones vector, and we add back B, we should get the all zeros vector. And if we take the Hadamard product of B and W, so we do the element-wise multiplication between a bit vector and its complement, then we should also get the all zeros vector. Great, but these aren't inner products, but again, we can kind of do this random linear combination technique to get them in the form of an inner product. So we, this should be Y0. This should just be bold Y. Ignore the zero here, sorry, typo. So we have our vector 1, comma y squared, so on and so forth. And then we take this this left-hand side of our equation and then take the dot product with y, and we should get 0. And then similarly, we do the same for for the second equation. If we take the Hadamard product of w and y, and then the dot product of that with b, then we should also get 0. So now we have our these equations written as an inner product. And so putting all these pieces together, we get 3 equations. These 2 that we saw from the previous slide, and this third one that we actually saw at the beginning, which is that this vector of bits dot product with D, which is essentially kind of representative of like the function, should equal to U. So these are the things we want to essentially prove. And what we can do is we can combine them again into one equation using that same trick, we sample a random z, and then we take a linear combination of these three equations, and these should equal 0. And then if you rearrange it, then you can also just get everything in essentially one inner product. And then again, we can take this inner product and use our inner product argument to prove what we want. So just another note here, this is not zero knowledge again, but you can go in and blind the vectors before actually computing all the equations. And that's kind of what we do in our paper. Okay, so I'm actually running out of time, so I'm going to quickly just jump through the experimental evaluation. So we implemented our scheme in Go. We used bullet proofs for the inner product argument, point proofs for the vector commitments, and we deployed the scheme on two summation Verkle trees, one that considered a universe of size 2 to the 256, and one that accommodated all 9-digit numbers. So this spanned like the US Social Security numbers. And here on the left, we have runtime, so public parameter generation, proving, and verification time. And on the right here, we have public parameters and proof size. So we see that as we increase the fan out or the arity of the sparse Verkle tree, the public parameters grows because those vector commitments are getting longer. But we do see that the proof sizes get smaller as we expect, since the authentication paths are getting shorter. And then here we have prove and verify total. So these are essentially like proving the totals. So that essentially equates to opening just the root node to like that n+1th term of the root node that essentially corresponds to the total sum of all the liabilities. And so as we would expect, the performance of verifying this total, since it's just a simple opening, is very efficient. However, proving grows linearly with the size of the vector. So in conclusion, we introduced a novel data structure for the POL problem. We presented 3 new zero-knowledge protocols over vector commitments, optimized the protocols to support aggregation, and we also implemented our scheme under 2 realistic use cases. So that's all I had prepared for today. Thank you so much for listening, and I'd be happy to take any more questions now if you guys have. Yeah, thanks.
Thank you.
Yeah, thanks a lot. That was great. So I guess I'll ask a question, maybe going into a little bit more detail about the sort of the Verkle tree and the vector commitments. I think you mentioned that it supports any sort of Peterson-like commitment. Does this include the sort of KZG style commitments, which I think I've also heard about being done for Verkle trees? Is it possible to basically do this entire setup with, you know, the style of Verkle tree commitment that would use the trusted setup that like the Ethereum Foundation has carried out, something like that?
Really, so I'm not, I guess maybe familiar with the KZG vector commitments, or maybe, yeah, was this maybe like,
Yeah, so my understanding is like maybe sort of like somewhat interchangeable between Peterson commitments and KZG vector commitments. I think the main difference with a KZG commitment, it's something that depends on sort of elliptic curve pairings, and it requires sort of a trusted setup in order to make the in order to make it work. But they have these sort of like ceremonies that they execute sometimes where basically a whole bunch of people will participate in a protocol to like derive some, some sort of special string that can then be used to sort of like go
Yep.
forward and have like a secure vector commitment at that point. Um, and I guess the benefit of doing all of this is like maybe that it's slightly more succinct or slightly faster than a Peterson commitment. So I was sort of interested if like that could be something that could sort of just be, plugged right in if you were willing to sort of trust that the trusted setup ceremony had gone well.
So I would say yes, absolutely. I guess the two requirements. So firstly, I want to say the point proofs that we instantiate our protocol with, and essentially we kind of really like our protocol, like our zero knowledge proofs, like really assume the structure of point proofs. But essentially, the vector commitments presented in that paper also have this trusted setup. So like all the elements are like of the form G to like some alpha raised like alpha to the
Yeah.
I. And so alpha has to be, I guess, like the public parameters are assumed to like be generated in a trusted setup. So I guess if it's anything like the way point proofs works, then yeah, absolutely. Like you assume that the trusted setup went well, and then you can use them in the scheme.
Okay.
Um, the one other thing I want to mention is that because you can have like a Peterson like a Peterson vector commitment. And I think if you just use those, then the opening proofs are not necessarily small. So the other requirement that we have is that we do have these like efficient vector commitments with like small openings. So that would be the other requirement. But yeah, trusted setup is also fine. Yeah.
Okay. Cool. Sounds good.
Mhm.
No questions from the YouTube this week, although there was someone who commented that they want us to make a Discord for our lab, which is fun. Maybe we should do that sometime.
Great.
Okay, I guess yeah, just any last questions. I think there's like maybe three YouTube viewers, or at least there were three YouTube viewers over the course. If they want to like ask any final questions, if not, I'm just gonna shut the stream down for now. Not necessarily seeing anything, so I think I'm just going to stop the end stream.